All right. Hello, everyone, and thank you very much for joining us in such great numbers. It's excellent. We are having our fourth training session today in our Presto training series with the founders of Presto. Today, again, joining us, Dain, working crazily hard the last couple of days on the deck. You wouldn't believe it. We had a lot of cool discussions and learned a lot again, of course, as always, and we're going to share this today with you. So today what we're going to do is we're going to talk about cluster sizing and performance tuning. Very important ones, as we had in the last sessions. You actually have a cluster of people that know how to write their SQL. You can get those queries going, and now you have all these users that want to use Presto. What are you going to do, right? Like, how are you going to size this up? Dain is the guy that knows all about that, and he's going to teach us a lot about this today. As usual, my name again is Manfred Moser. You know me from the last training sessions. I'm just a hacker, writer, and developer, and I help with Presto these days. And Dain started Presto with Martin Traverso and David Phillips and Eric over 8 years now ago. So it's been a long run. It's quite amazing. And he's now CTO at Starburst and knows the ins and outs of Presto. And he's going to share some of the wealth of his knowledge with us today. So it's going to be pretty amazing. In our class today, as usual, I'll just quickly go a quick review about Presto, but then we're going to talk about cluster configuration, like what kind of machines, how many machines, what size. We don't talk about workload tuning, making the queries faster, sharing resources, all sorts of things, all the things you need to know to get your cluster up and running and to a performance that satisfies the needs of your users. And that can also, we'll discuss that as well, can be different. As usual, we have a break session in between, questions at the end, but also ask questions anytime during the session. I will sort of like verify questions, answer them in the chat in between, interject. We'll also have those dedicated Q&A sections afterwards. To do so, use the questions features of our meeting section. So just type away, and hopefully I get to see them all and type back, and otherwise we'll talk about them. And that's that for the session. Otherwise, of course, afterwards, we will make the recording available and we'll make the slides available. So you can also sort of like go slow through it again and try it with your own cluster. Obviously, you won't be able to like follow along with your own cluster. It doesn't go that quick on sizing up a cluster or changing configs, restarting, that kind of stuff. So just focus, pay attention, learn from Dain, and use the stuff that we provide, like the downloads for the video and the slides and all stuff later on with your own cluster and experiment. You'll see there's a lot to learn, and there's a lot of complexity there, but you'll find all about that out from Dain later. Just a quick overview. You probably know about Presto already. In case you don't, Presto is basically a SQL query engine. That means you can query with the SQL standard query language into all sorts of data sources, including, of course, all sorts of Hive sort of resources like distributed object storage systems and cloud storage systems, but also other data systems, databases like relational databases and so on. And Presto is this query engine. So it just runs the queries, asking the questions to the underlying storage systems, and it scales dramatically, and that's what we're going to learn more about. Very successful open source project, over 2,500 people on just even our Slack channel. It's like crazy busy there all the time. We just got a new release with crazy new features again. Just yesterday, Iceberg Connector, Salesforce Authentication that we promised in our recent session last time, actually. So Presto is everywhere. You should use it, and today you get to learn how to query it. How to tune it a bit more. In general, why you want to use Presto? Well, because it allows you to unlock all that data that's in those proprietary systems. Your users can all use queries written in SQL, which they already know, and also the tools that support SQL like Tableau or Apache Superset or some other system. All of them support basically SQL in their analysis. So that's what you want to unlock today. You have the one consumption layer with Presto where you query all of it at once, multiple databases across joins and all sorts of other stuff. But How are you going to make this actually go fast is what we're going to learn today from Dain. So without further ado, rock it, man.
All right. So I'm going to turn off my video here so it's not so distracting. All right. So today I'm going to go through cluster sizing and in the beginning, and then the second half, we're going to go through a bunch of stuff on performance tuning. All right. So in this first section, we're really trying to answer two questions. How big does my cluster have to be? So like, how many vCPUs? How much total memory do I need? And then how do I divide that requirement up into machines? All right. So in general, you could just, this is my favorite strategy for this is literally just go and create a really big cluster, bigger than you think you need, and then set up all your data sources, start onboarding users, make sure everything is stable, just have more resources than you need in the beginning, and then try and tune it. Don't try and set up a cluster, learn Presto, and try to be efficient in resources all at once. Do them in 2 steps. Spend a little bit more money up front, and then tune it. And then as you grow into the cluster, as more users come on, like you already have the resources available, and you have a much better understanding of what you're going to do. This is the easiest approach, and this is kind of a general strategy that should just work. But unfortunately, almost no one likes this strategy, especially like the bosses who have to pay the bills. So we're going to talk about how to pick how big your cluster can be, or even more importantly, like you may not have any idea what the right answer is, in which case like this will help you start to build a mental model around how you're actually going to size a cluster. All right. So before we get started, I want to like just break some assumptions. So one of the biggest problems we have, and I spend a lot of time helping people on Slack, is that people think Presto works like other systems out there. And Presto is unlike almost every system that people have used. It's very similar to a bunch of systems that people have not used very often. So the first most important thing is that Presto is a distributed computing engine. This means that when you run a query, we're likely, and we're going to try to use all the computers because we want as much resource as possible to finish the queries as quickly as possible. So most people have like worked on systems where like there's one computation per HTTP request. I'm going to generate one web page. I might do 10, queries to generate that web page or hit a bunch of caches. Well, in Presto, we're going to use all the computers in the cluster and do one computation. So people that are expecting like, oh, I can just kill a machine anytime and it's only going to affect a few users, like, no, you're likely to affect basically all the computations that are going on. So like, just different. Presto is designed to use all the resources. We want queries to be as fast as possible. The faster we finish a query, the faster we can start on the next query, and we get the most leverage out of our resources. And this will be a recurring theme throughout this is leverage of resources. So we're going to use all the memory, all the CPU, all the network. If you don't want Presto to use all the network, you need to apply some resource constraints at the OS level, at the switch level, in your VLAN. Otherwise, we're going to use it because, in our opinion, you allocated it to us. So like that's another just really big thing people just don't understand. And it's like a core design philosophy of Presto. Anyone who comes from a Hadoop background expects to have a whole bunch of processes on each machine, each process doing like one tiny part of the query. No, so Presto uses one process per machine. Like you should run one process, one OS on one machine. And that way we don't end up with, and I'll go into details on this, like lots of overheads, but also like we designed the system for multi-threading, for all these like advanced things. And so we expect to have one big process. And we'll get into kind of the rest of this around multi-threading, etc. But that's a really big part of the Presto story and a big part of what makes Presto fast and efficient. All right. So
just before you jump there, Dain, there was a very good question from William before, and I want to clarify that. When you said in the first slide, you said, don't try to stabilize and tune at the same time. I'm pretty sure you mean that don't add new catalogs, new users, new BI tools, and all sorts of other config changes at the same time as trying to tune it, right? Is that what you mean?
Yes and no. What I'm really getting at is, so tuning your cluster when it's not stable is basically impossible because you can't tell what's going on. So it's not only stable in terms of like, you want to have like a stable workload, but also you want to make sure like, hey, is my cluster crashing because it's out of resources? What you want to start it with is too many resources and then work your way down to just the right number. Starting from the bottom and being like, oh, what's the smallest number I can add up, just leads to user frustration because your systems appears to be unstable. And having, you know, if you're going to introduce Presto into an environment, it's a new thing and you need it to be stable in the beginning, because if it's not, users will assume it's unstable even after you fix the problems. And they'll always be like, well, I don't want to use it, it crashes all the time, blah, blah, blah. And like, that shouldn't happen. You shouldn't be having machine crashes. If you do, it doesn't have enough resources, it's misconfigured. So start with too many resources and then narrow down the efficiency.
Okay, awesome.
All right, so I'm just gonna throw this out as baseline advice. Again, I help a lot of people on Slack, and we can spend like a couple of hours trying to work on configs, and then we figure out like, oh, they have spilling enabled in the OS. Well, the answer is spilling just flat out does not work with Presto. So go and disable your OS spilling. The JVM was never designed for spilling. It uses a compacting garbage collector, which is always moving stuff around. You don't really have cold sections. Also, like, spilling means you're throwing memory on disk. Do you even have a hard drive on your computer? If you're in the cloud, you're probably using like the Elastic Block Store or the equivalents in some of these other environments. Then you're spilling across the network, which is just terrible. Like, it will literally, like, your machines will be running along and then they'll start to spill. And the common thing is like, oh, my whole system froze. And it's like, okay, well, that's because you're now spilling and it's, you know, loading blocks in and off the network for you. So just disable it. It isn't going to work, and that's fine. There's a thing in Kubernetes called the runaway process detector. Basically, if you assign a pod and you say, hey, you get to use 8 cores, if they see that it's constantly using 8 cores, it's like, oh, well, that thing's like doing too much. It's runaway. It's just spinning out of control, and it'll kill the process. Well, Presto is going to try to use all the cores at the same time and max out the CPU. So like, it will definitely trigger the runaway process detector. It'll kill your processes. Your cluster will feel unstable. So you need to turn that off for Presto. Also, super important, you need to upgrade regularly. So we're constantly fixing and improving things. There's actually, if you're a Glue user, there's an important fix in the release that just went out that makes Glue more efficient and makes it less likely that you're going to get throttled by Glue. And if you know anything about the Glue meta store, throttling basically kills your performance. Like, you know, people move off of Glue because they get throttled. So there's some important improvements there. And there is a common story. Releases come out typically like every other week. And there's always important things in there. So make sure you have a plan to upgrade regularly. I suggest at least once a quarter. And pay attention, there's critical security fixes. As I mentioned in the previous presentation on security, you need to be running 3.3.7 or newer, or a version from a vendor. Well, except I don't think EMR has quite fixed their version yet. I'd have to check again. but I think everyone else has patched their versions. All right, so now I'm going to get into the important part of this one, which is cluster sizing. All right, so when I think of cluster sizing, I'm really thinking about two big things. Do I have, how much CPU do I need, and how much memory do I need? So CPU is the thing that's going to process your data. It decompresses the files from your Hive store. It's running the joins. It's running the aggregations. The more CPU you have, generally you get shorter queries. There are limits. We'll talk about that in a second. Memory is a little bit different. It's you either have enough or you don't. So like if we're going to run a join, we have to load one of the tables into memory. If it doesn't fit, then your query is not going to complete, or you're going to spill, and we'll talk about why you should never turn on spilling because it sucks. So you either didn't have enough memory or you don't. Now, I think about memory as limiting concurrency. So, and we'll talk about this a bit more, but really in any environment that's running Presto, you almost always have a bunch of users running at the same time, and memory basically controls how many of those queries can run at the same time. So, you know, if you go to a cluster and you like double the CPU and keep the same amount of memory, like generally you can run the same amount of, you can run like double the workload using the exact same memory, but you can't do it concurrently. So, you know, you would run, you know, a full copy of the workload and it would generally complete in in half the time. And then you'd run another copy of the workload and it would complete in half the time, but you couldn't run them all at the same time. So you can't double the concurrency without basically doubling the memory. If that makes sense to everyone. All right, so I'm going to dig a bit deeper into CPU. So Presto is generally very stable when it comes to amount of CPU required for a query. Now, it'll change across versions. It would change if you reorganize the data, but if you take the same query on the same version on the same data set and you run it like 10 times in a row, what you'll see is after like maybe the second try, because maybe it'll have to warm something up, like you'll use almost the exact amount of CPU for every single query. And so if you want to know how much CPU is required, like you run it, you look in the CLI, you look in the UI, and it's like, oh, this used like, you know, 1 hour of CPU. Now that's the amount of CPU core time it used. So 1 hour is 60 minutes. If you had 60 cores in your entire cluster, then you would the query would have ran for, you know, something like a minute or so. Each core allocating a minute of the CPU time. So generally, and this is a very broad generalization, if you double the amount of CPU in your cluster or available to a query, it's going to take half the time. Now, there are limits, as I'll show in a second, but it's easier to think about it. If I run 2 copies of a query and I have the exact same amount of cores, they start taking longer. And this is actually a really common question in Presto is like, hey, I ran a query and Presto's amazingly fast. It completed in 1 minute, but then I ran 10 queries and they all took 10 minutes. So what's happening is, if you look at this picture here, I have, let me turn on the little pointer guy. There we go. So in the first one, I only have 2 cores and I have like 8 little units of work. And basically what happens is they stack up on each one of the clusters and then on the cores, and then they start basically burning down these little jobs. If I had 4 cores, then each one would end up on average doing about 2 pieces of work. If I had 8 cores, then they all line up and we get like, this is and for this query or this workload, this is as fast as it can get. If I had 16, I just have 8 more extra empty items here. And so like it would take a fixed amount of time. So like Presto divides its queries into units of work, and there's a certain number of these, and the fastest a query can go is basically the cost of, you know, the longest part of those works. So what I'm showing here is a super simplified model. You know, I made all these little boxes the same size, and that's not real. In most cases, like some parts of, you'll go to take a file and divide it up into 8 units, and then like, 7 of the 8 actually end up, having effectively no data. They get filtered out immediately, and one of them has all the data, so maybe it takes longer. So really simplified model. The important thing here is that we're trying to, what I'm trying to show here is that as you add more work, the more CPU you have, it's going to spread out that work, and you generally get faster queries, or you can run more concurrent workloads. And I mean, the other thing that's awesome about CPU is that like we have a scheduler in Presto, and therefore what it'll do is it has a prioritization system, and it'll go through and start prioritizing queries. So in this first case, if I actually had 2 queries that each took 4 units, the system's actually going to try and fair share. So each one is actually going to, using the normal scheduler, is going to take the full length of the stack. So it'll put like basically 1 on 1 system, and it'll fair share the CPU. So as opposed to if the ordering were different, like maybe one query completes immediately, the other one query then just sits in a queue for half the time and then actually runs. So there's a lot of complexity going on in terms of ordering, etc. But the general is more CPU is going to reduce the overall query time. All right, I'm going to jump on to memory now. So memory is unlike CPU. CPU is easy because you can time slice it and like basically take a job and be like, oh, I got something more important, I'm just not going to run this computation for a while. Memory is like you load it into memory, like that's a resource that's taken, and you really don't have anywhere to put that memory. Again, we can talk about spilling, but spilling's not really a great idea. What is actually using up memory? So if you look at your query, there are a couple of really common structures that use basically all the memory of the query. So there's joins, group by aggregations, ordering, window functions are the big ones. There are other ones, but these are the most common big users. And actually, join and group by are typically by far the biggest. The other ones are normally not as big, or normally not as, like, most people don't know how to write window functions. So in a join, we basically, I'll go into more detail on this. We take one of the 2 tables that we're joining together and we load it into memory into a distributed hash table. So like that could be quite a bit of memory depending on how big that table is. For a group by, you have a hash table that has the group by keys, and I think this is covered in David's section of like how group bys actually work, but you have the group by keys and then you have the aggregate values. Normally aggregations have like a fixed size, like an average has a sum and a count, but there are some aggregates like array ag, which is literally just all the values concatenated together. So it takes up a huge amount of memory. It's effectively loading the whole value, the whole table into memory. Ordering, you have to load the result sets to actually store it. That's more complicated. Windowing is a combination of a partition and a sorting window. It's basically a combination of like grouping and ordering. Query plans in this case really, really matter. The join orders, it's really important that if there's 2 tables, we're loading the smaller one into memory because it will literally take less memory. The other thing is that joins have effectively phases to them. So if you're doing 10 joins, do you need to have all 10 hash tables in memory? Well, the query plan can influence how many you have concurrently. I'll talk a little bit more about that in the second section when we get into performance tuning. All right, so how big does my cluster need to be? Well, unfortunately, the answer is the worst answer and the most common answer you'll get out of every database vendor you've ever run into, which is it all depends. And why does it depend? It depends because in the last section you saw like you're your users are providing this program that says, hey, I want to join these two tables. One of them's got to be into memory. Well, you could have a cluster where the users never ever do joins. They never do group bys. They're literally just doing like, you know, a full group of the table, and they're just doing counts, or they're just streaming data in and out, in which case that cluster needs basically no memory at all. It's just like all CPU bound. On the other hand, you could have a workload where your users are always trying to load two ginormous tables together, like it's called a fact-to-fact join, in which case you're going to need tons of memory because every query is going to take a huge table and throw it into memory. So what you end up having to do is you have to go through and you have to figure out like what are the queries people are going to run. And if you're lucky, you have the exact queries and the exact data, you set up a cluster and you start experimenting and sizing. So you run the query, you measure it, and then you start to make guesses about like, how many of these am I going to run at the same time? Am I going to run 2? Am I going to run 4? If so, then I'm going to need, you know, 4 times the amount of the peak memory of those queries. And then of course you'll need some buffers because like sometimes the peak memories is not totally stable, or like some other user comes in, the data is going to grow, etc. So this is like a really tough thing. And our goal with this is to actually come up with a really good estimate. So this is actually something we talk about a lot with at Starburst with our employees that are doing sizing, is like, we want to come up with good answers, because if it's too small, then, you know, you go to your boss and you're like, oh, I need a 10 node cluster. Turns out you need a 20 node cluster. Like, that's a big step up in price. Your boss is going to be unhappy with you. Also, if it's too small, your users are going to be unhappy, and that might actually be even worse. It might damage the reputation of your the organization that's hosting this cluster. If it's too big, your boss is mad because, you know, you allocated a bunch of resources to something that isn't actually going to use those resources, or you're wasting money, etc. They're a little bit, in my experience, less happy than if it's too small and you have to go back and ask for more money later. So one of the really big things here is, and you see this in these questions, is expectations. So your users are going to have some expectations of latency. Sometimes it gets, you know, they're building it for an application and they have an exact time. That's very rare. But normally, like, you know, people are going to want small queries to work immediately. Medium queries should take like a minute to 30 seconds to a minute. And really big queries are like, yeah, they shouldn't really take more than like, you know, a half hour, an hour, or something like that. So trying to figure out what those are, and again, it helps if you have users and you can play with it, but you need to explore that space, because latency and consistency of that result in something that you need to think about, which can be over allocation. So if you have the expectation that all your queries are going to take, you know, 1 second, then you need to make sure that the CPU is there to run that all the time. And, you know, if, you know, you have enough to run 10 concurrent queries, if you need 11 queries, then like they're going to start to queue up and they're going to get slower. If, you know, and you can't just go add new machines, because, you know, in a cloud environment, it's going to take you several minutes to add those machines, and you're talking about like a query that takes 1 second. So when you need to make sure that you have the ability to run 10 queries at 1 second, if there are no queries running, then you still have to have the hardware sitting there idle, available to run those 10 queries. And so you end up with this level of over allocating the resources to deal with you're planning for peak when it comes to low expected consistency or very consistent queries, because you basically have to have all the hardware sitting there, because at any moment 10 queries could drop. So
that's also related to a question about that Hugo was asking how dynamic scaling works with Presto. He's sort of thinking it goes back to the old way of, like, you know, old practices, but that's essentially what it is, right? Like, to some degree, if you want like predictable performance, you have to have things ready to run, right?
yeah, so the question is, I mean, we'll just start with, like, assuming you're in a cloud environment, the fastest you're going to be able to add a machine is a couple of minutes, depending on the cloud. You should basically expect 5 minutes. So you need to predict 5 minutes into the future how much resources you're going to need. So as your day ramps up, like, yes, you can predict that. But if your workload is really spiky, there's really no way to predict it. Like, you just have to have the hardware sitting there. I don't know if that really answers the question.
I think it's a good start.
Okay.
We'll probably end up discussing it a bit more later.
Yep. All right. So what if I don't know the answer to this question? Like, I go back and I start looking at this, like, I don't know how to answer this. I don't even know how to begin to collect this information. All right, there's basically 2 roads to this. Engage a vendor. Like, we have people who work for Starburst that's their entire job, is to engage with customers and figure out how big their clusters are going to need to be. Like, we have to know it, because, you know, when we're selling people stuff, like, we need to know how much to actually sell them. We also need it so we can predict our sales pipeline. So it's like something that everyone needs. And so we have people who do this all the time, and they know how to ask the questions, they know how to interact with people. Any vendor selling Presto should be able to do cluster sizing. If they don't, run away. Like, this is like a job everyone has to do. So the other side of this is, you don't know. So what you do is you ramp it up. And so this is what we did when we set up the clusters at Facebook. We built a pretty big cluster. We put hard limits on how big any query could be, because we didn't know how big a query could be. So we would just be like, no query should be bigger than 1 terabyte of memory and should run longer than, I don't know, an hour. Or, you know, maybe an interactive cluster, it's half a terabyte of memory and 20 minutes or something like that. So we just guessed what we thought would be reasonable. And then what we would do is we would find one team that wanted to work on Presto, and we would onboard that team and see what they're doing. And then we try and find a team that was very, very much not like the first team. So the first team was all people doing interactive through Tableau. We'd go find someone that was using the command line or a dashboard system. And so, like, we would onboard diverse sets of users, and we would measure and resize. So this takes longer, but the goal here is to have a good experience the whole time, and to be able to work with these different customers and build a mixed workload, etc. You need to, of course, have buy-in from your bosses, because you're going to be constantly growing this cluster as you onboard more people, and you actually really the budget's going to be. So they're going to have to, like, pick a big budget. So they're going to probably have to have buy-in from, like, up the chain, that this is something that's going to grow. So, like, make sure everyone be aware of this being your plan. Again, don't surprise people with it. All right. So unfortunately, that's about as much as I can say about how you size a cluster. You're going to have to measure your workload. You're going to have to guess how many queries are going to run concurrently, or know that. And then you basically start summing it up, and then you're, okay, I need this many vCPUs and I need this much memory. So huzzah, we're done, right? No. So we know the total amount of CPU, the total amount of memory, but we don't have computers that are that big, so we have to figure out how we divide those into individual machines. All right, so I'm gonna dig a little bit into some really things that to understand about, you know, machines and how they affect Presto from the Presto perspective. So the way I think about memory is I kind of think about this picture off to the right here. So I get a machine, which would be like this outer gray box. It has this OS layer on it. It's got memory allocated to the kernel and network buffers and other processes that are running in my system that are all going to take memory from me. And then I'm going to have my one big ginormous Presto process that's going to be running in the Java virtual machine. Now, most people don't understand how a Java virtual machine works. Even many experts in the Java programming space don't really understand what's really happening inside of a Java virtual machine. So the Java virtual machine, everyone who deals with it is like, oh, it's got this memory setting. You set the heap size, the XMX. You're like, my memory is 200 gigabytes, right? And they're like, great, I have, you know, 200 gigabytes free in my OS, and I can just allocate 200 gigabytes to my Presto process. No, 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 that's not how it works. The heap is one part of the memory used by the JVM. It is by far the biggest part, but there are all these other things that you have to leave resources available for. So every thread in the JVM is going to have a stack for allocating like local resources. Each one of those is, I don't know, a megabyte or something. I don't actually know. You have to look it up. So you end up with a bunch of memory allocated to the thread stacks. Java takes and the code that you're actually running gets compiled down to like native structures. That native code actually takes up a lot of space, especially in Presto, because we're generating code for all these queries. That's a lot of code in memory. That's going to take up some space. Typically, this is like 500 meg. The garbage collector has data structures that tell the system basically where all the objects are, how those objects are divided into groups, how those groups refer to each other. It's pretty efficient, but it's not free, and it's not part of the heap. And then another really big area that people aren't aware of is there are these native buffers. So the Java programs will allocate direct native memory for things like IO buffers off of the network stack. So you hand the network stack an IO buffer and it reads like, you know, a megabyte of data into it. Well, that's a buffer it's explicitly not part of the heap. And the JVM actually allocates these for itself, and the Java program will allocate these for themselves. There are config options in the JVM to control the size of this, and you need to set them. They're in the, so in this presentation, I don't go into exactly how you configure the JVM in Presto. It's documented in our documentation. Copy those configs. Like, they're good values. And the other really important advice is don't do a lot of configuring of your JVM. Like, people go crazy with it and they actually end up detuning it. Like, it's pretty good out of the box nowadays. So anyways, after that, we actually get to the heap, and that's the part of the memory used by the Presto program itself. And the vast majority of that is allocated to your queries. But there is a significant portion that is not directly attributable to a single query, or it's simply not tracked. So there's shared things like shared buffers for our network stack between machines. There's also, like, as you're processing things, we might be building a temporary page of results. Like, it might be, you know, a couple of megabytes or something like that. We don't track all that. It's too much work, and on average, it just kind of works out. We're basically tracking the really big structures. So, all right. So this is kind of like the mental model I want you to have in your head. So when you're looking at a machine, the first thing you want to figure out is, okay, well, I rented a box that says it has 256 gigs of RAM, or I got one from my admins in a data center. Like, log into the box and figure out how much memory it really has. Did someone stick a virtualization environment on there that went and stole like 10 gigs of RAM? Are there a bunch of other processes on there? Like, this was a huge problem at Facebook. Some, enterprising new employee would go and write some program to do an amazing thing and then deploy it on everyone's machines, and it would go and suck up like, half a gig of memory for no reason. So go figure out like how big is your log collection system. Some of them are like use a crazy amount of memory. Are there network buffers? Are there huge, sections of memory allocated to the network DMA because your network card doesn't have any memory? I mean, it's surprising. So go figure out how much is actually available to the OS. Disk buffers and network buffers really only start to get allocated when it gets used. So you're going to want to go back and look at this once you get the Presto process running. So then what you want to do is allocate 80% of what's left to the JVM heap. Now, the big question is, hey, what's that other 20%? Well, that other 20% is split between everything else the OS is going to need. So this is all your, so typically like the OS overhead for buffers, etc., like all that sort of stuff. It's the OS overhead, and it's all the rest of that JVM overhead, like the native stacks and your GC structures, etc. Actually, let me think about it for a second. Actually, so normally what we're saying is 80% of the total machine size. Now, and a minute ago, I actually just said 80% of what's available to the OS. So this is a rule that we generally use is 80%. If your OS has a ton of processes that are sucking down memory, you're going to have to allocate more to the OS. If you don't have a lot of this and you have more free space, you can try allocating it to Presto by increasing this. You need to be really careful. In this picture here, see, I say you must have free space. See how there's this little space down here at the bottom? So in basically every OS, if you have the heap and it's allocated all the way here, and then one of these structures comes along, some other process, something else, sorry, in here, like we allocate some extra thread stacks and there's no free space, the OS is going to kill this entire process. And you don't have control over like what the GC is going to do for its data structure. So you have to have free space, and you need to leave that there. Otherwise, you make your system unstable. And it's worth buying a few extra machines to make sure your system is stable. So go to your machine, in general, allocate 80% of what the machine actually has after virtualization, and allocate that to the heap. Then inside your Presto config, allocate 70% of the heap to Presto. Now, to the general data pool. Now that is 70% of the heap for the tracked data structures that are directly accountable to a single query. It doesn't mean that Presto is wasting 30% of memory on its own internal junk. It just means those are the shared things that are used across all queries, and it's the shared stuff used across all the queries, and there's a bunch of stuff that we don't track because it takes more CPU to track it than it's worth. So in your mind, think 70% tracked, 30% untracked, as opposed to 70% used and 30% wasted. So I will commonly get a question here, which is like, hey, that seems like quite a bit. So you have 128, you go down to 100, that gets you your 80%. then you have 70% for query memory. And people are like, well, how does that compare to Yarn and with MapReduce and Tez and Spark? So we have a few employees that used to work for Cloudera and Hortonworks. So I asked them this question, like, what are their recommendations? So the recommendations that they have is commonly is for Yarn, they get maybe in a really super tuned system, they might be allocating 70% of the OS, 70 or 80% of the OS to Yarn. But in general, what they end up configuring at bigger clients is they actually bring that number down because trying to allocate too much destabilizes the system. But let's go with 80%. So that's what Yarn. Then Yarn has a bunch of JVMs. In each Yarn environment, they allocate 80% of each one of those, 80% of what Yarn gets to the JVMs. So they start off with something more like on this 120, on this machine, they would get 80% of 80%, but that is to this part. So they are down near like 80 gigabytes that they're actually allocating to the JVM heap. Then inside of their heap, so much of that's actually going to be used for, you know, the actual running of that Spark job, and a chunk is used for the JVM overhead and the same sort of thing. So we are pretty confident that we end up actually being able to use more memory for Presto queries. And the reason for that is that we're only running one JVM. It's a really big story, is that we get the JVM overhead once, we get the OS overhead once, and we're effectively able to share memory across all these things. So we do, I believe, much, much better. I'm going to spend a minute explaining how joins work, because it actually affects lots and lots of the discussions later on in this presentation. All right, so in Presto, the way a join works is unlike most of those other MapReduce-like systems. A big hash table is built, and then we have a bunch of threads that share the hash table, and that's the thing that's fairly unique in the big data space. So because we're using a big hash table, we can have multiple threads all probing this hash table. It's a big read-only thing. So what we do is we read in data, it goes into a buffer, and then each one of these threads is just pulling out a chunk of the rows, and it's doing a lookup. In this case, it's turning zip codes into city names. So it's just like, okay, what's 94301, gets Palo Alto, and it throws that into an output buffer. And so we can scale up and add as many threads here as we want to probe this. We can scale this down. But what happens here is that we're able to leverage this memory. So if I have to probe 1,000,000 rows here, and I'm using one hash table to one thread, then it's going to take, that thread has to process through those. But I'm actually able to throw more threads at it, which means that I can finish that 1,000,000 rows faster, which means I can free that memory up faster and use it for something else. So the multi-threading actually leverages the memory, because I can clear the memory and use it for something else, which means I effectively get more usage out of that memory, if that makes sense to you. So speed is actually really important to memory efficiency. If your things are slow, they're sitting in memory longer, and therefore you can't use that memory for other things. You have to buy more memory. All right, so that was inside of a machine. Now, a distributed join, basically what we do is we have a bunch of machines reading the smaller table. And then what it does is it takes that each row and it hashes it by the key and mods it by the number of machines we have and just sends it out. So what ends up happening is, like, if we're distributing by user ID, all of user 1 will end up here, all of user 2 will end up here, 3 ends up here, 4, etc. assuming we only had 2 machines. And so this gets sent in, and then there's a bunch of parallel threads that build this hash table. And then on the probe side, we again apply the same hash key. So all of the ones for the build hash table and all of the probe end up on the same machines. And then we do this multi-threading. Okay, so this is a really, really simple hash join. So at the end, we end up with each of these machines end up with 1 over n being the number of machines, number of rows. Now, in Presto, this is going to be a machine, this is going to be a machine, and then these tasks here can be spread out amongst these same, these same machines or different machines. These are just generalized tasks, and they can run anywhere, and they can run in parallel on threads. So each machine is going to end up with 1 over n of the build rows and 1 over n of the probe rows. Okay, so that was a very long way of explaining why skew is such a big problem. So in the assumption of your build is that you're distributing on something that's actually has a fairly even distribution. And therefore, when we're doing like a join on users by user ID, like every machine's going to end up with basically the same amount of rows. And same thing if you're doing like a group by, you're going to end up with like the same amount of rows going to a machine. Well, what happens when some of those keys have more rows? So, you know, really active users are going to see a lot more pages on your website. They might see 100 or 1,000 times more pages. Now, if you have a really big website like your, you know, Facebook, you have so many users that, you know, if you know, this thing's basically going to, every machine's going to end up with on average, I know something like, let's say 100,000 users or something like that. On average, like if you pick a random 100,000 users, they're going to end up with basically the same amount of rows. Okay, so that's normally okay. But a really common scenario that was super common a few years ago was people would assign user ID 0 to mean, hey, this user isn't logged in. And then like half the rows or a quarter of the rows would be logged out users. And they'd all have user ID 0. And guess what happens? Some unlucky machine ends up with half the memory. Okay. Now, this was super common before people switched to like device IDs and things like that. So you have to be really careful of this because it's going to have a really big impact on what's going on. You get an uneven memory distribution, and it could literally not fit in the memory on that machine. If you have a really big table and half the rows are, you know, you're like, I'm going to distribute this over 100 machines and half the rows go to one machine, it's not going to fit. Your query is going to fail. Now, the machine isn't going to crash because we have memory tracking, but the query is going to fail. You know, in general, it's not that extreme. In general, you end up with like, oh, I ended up with twice as many rows on one machine or 3 times. And what can happen in many systems is that one chunk of that one worker ends up taking 2, 3, 4 times as long as everyone else does, and it makes the queries really slow. And again, slow queries hold stuff in memory longer. It draws a lot more resources out of the system. You can also have problems like it produces a lot more output rows, then the network gets saturated on that machine, etc. So it can either be, if it's on the build side, it takes up a lot of memory. If it's on the probe side, it can take a lot more CPU to process those rows because it's getting like 10 times more rows that everyone else is getting. Group by is actually an interesting case. Skew and group by can actually make group bys more efficient. And that's because on individual workers, they're actually doing a partial aggregation. So they're, you know, taking and they're grouping the rows and compacting them down. And typically there are a lot more of those partial workers, you know, because they're like hooked directly up to a table scan, than there are the ones doing the full aggregation. So you actually spread that work out and it ends up making your partial aggregates more efficient. Now, that's true of most aggregations. It is definitely not true of aggregations like ArrayAg, in which case, like, you end up with ginormous arrays. So you have to be really careful of ArrayAg. It's a pretty dangerous aggregation. All right. So the reason I explained all that is to make this statement. You want to use bigger machines. And this is very, very much unlike most other systems out there where people want to use tons and tons and tons of small machines. So what we want is we want to take our total cluster requirement and divide it into a smaller number of bigger machines. Now, the reason for this is from the first section, we have less memory overhead per machine. So a bunch of those data structures, like at the OS level, are the same size regardless of how big the machine is. Like, you're going to have one log sending process, and it isn't going to be take up like twice as much memory because you have twice as much memory on the machine. It's just a fixed size. So you have less overhead. A bunch of the data structures in the JVM aren't scaled with the size of the JVM. So therefore, like, if you have more memory, then you have less of it is allocated to this overhead. But that's only a small win. The big win is big machines mitigate the problems of skew and mitigate the problems with the scheduler. So in terms of like the scheduler, Presto is basically sending work out to these machines, and it doesn't have up to the minute information about the machines. It has old information, and so therefore it can make bad decisions. But if you have a really big machine with like a bunch of cores, then it'll balance out in the end because there's more cores to kind of like mop up and like do some extra work, and it means that, you know, adding an additional unit of work isn't going to take up like a significant portion of the machine. It takes up a small portion. So like those mistakes aren't huge mistakes, they're little mistakes. And that's kind of what we want. For Skew, this is huge. Basically, if we end up with a big hash, if we end up with like, you know, half the rows going to one machine, well, I can allocate like 30, 40 cores to processing that join. And the rest of the machines, they'll just allocate 1 or 2 cores, in which case like the query still finishes really fast. And so it makes up for like this skew problem. So, you know, this multi-threading stuff is something I added to Presto like 4 years ago. And we had a huge problem with skew at Facebook. And the day I rolled it out, I went from having questions about skew like 1 or 2 times a week to like once every 6 months. And, you know, that was great because, you know, I want to write code, not answer people's questions about skew. So there's a bunch of other things like, you know, you get less overhead from broadcast joins because the broadcast joins replicate that table to every machine. So if you have less machines, then obviously you have less memory used for those. The coordinator has to talk to every machine to figure out how much work it has, etc. If you have like 10 times as many machines, the coordinator's got to do like all this extra work. So bigger machines. Now, what do I mean by bigger machines? So the machines that we used at Facebook were actually very close to this. They were 256, and then I think we had 48 cores, real cores, not hyper-threaded cores. So that's a pretty good number. And so if you look at this chart, I listed the cores, the memory, and the network. Now, this is really important that if you notice, the network is very much aligned with the exact amount of cores you have. That's because all these machine types, these are all AWS machine types. These machine types all actually have 48 cores in them. They just have less amount of memory, and then they slice it up to different amounts for each OS that they divide it up into. So one issue when you're like, oh, I actually want to have a lot more memory for these 16 cores is you're getting half the amount of network. Now, this is normally okay because, in Presto, basically every core is going to require a certain amount of data to be able to be busy. And as you add more cores, you need more network because you need more data to keep those cores busy. And this ratio they have here is pretty good. But you have to realize that as you go down to smaller numbers of cores, you're now siloing your network. So again, going back to that issue of like Skew, if I have Skew in the amount of data that I need to read, then it hits this machine that only has 16 cores. Well, I only have 10 gigabits of network. I may actually be sitting there idling because I can't get it through this 10 gigabit straw. This becomes even worse when you're talking about, this 8-core machine and you only have 5 gigabits of network. So again, I prefer balanced machines and bigger machines. It's possible that this is actually more memory than you need, but this is a good place to start. The R5, the R series, unless you're doing really huge joins, like these are really, really big machines in terms of memory, in terms of memory to CPU ratio. So if you're doing big fact-to-fact joins, or you discover like, hey, I just need more memory, like the R5s are good. The Cs are a little bit, they're interesting. Like the biggest machine you get is 96 cores and 192 gigs of memory. If you could fit in these machines are super affordable. But if you don't fit, then your queries fail. So be careful. And that is a ton of cores to keep busy with 25 gigabits of network. So be careful. Just a quick comment. So I know I saw a blog post about measuring Intel, and they were saying that AMDs actually get less performance. I would actually try that out because I don't believe the blog post, and it could save you 10%. Of course, these machines I think are less prevalent, so you might have a capacity issue with it. The new Gravitons are really cool, and I know some companies have been trying them out. These are, sorry, these are Amazon's ARM processors. I would expect Microsoft and Google to follow with ARM processors of their own. You get 64 real cores. You don't have hyper-threading, which my guess is it ends up performing more like a hyper-threaded system. But the big news is that you're getting cost 20% less than the equivalent of this. So it's a 256 with 64 real cores as opposed to V cores. Same 20 gigabit network, but for 20% less cost. Heck, give it a try. And if it does work out and you get the same performance, let me know. Come write a blog post about it. I'd love to see more write-ups about the Gravitons. I'm excited for the cost savings. All right. Okay, I'm going to quickly run through some additional thoughts because I'm running a little long. Someone's going to ask, why don't you do sort merge joins? Okay, come back to read this slide later, but as a summary, sort merge joins are only faster if you're not sorting. There's a bunch of research on this. You can go read a bunch of papers on it. But the reality is that sorting is actually really expensive. And it typically requires things like disks to throw temporary space on, etc. And so people always ask about this because this is actually the only join that Hive and Spark do efficiently. And the reason they do sort merge joins is because that's how MapReduce works out of the box, and they didn't have to write the sort merge join. It was just provided by the MapReduce system. They were going to write it out of the box like we did. They would have definitely chose distributed hash tables. They're just much more efficient. There's also a big issue with parallelism. Like it's difficult to divide up these sorted structures and dynamically divide them up. As you saw with our hash table, we can just simply throw more threads at it whenever we want. All right. Someone's definitely going to ask about spilling. basically the way spilling works is for a hash table, for a join, we take part of the hash table and we throw it on disk, and then we take all the rows that would match that part of the hash table and we write those to disk. Then later we load that part of the hash table off disk, and then we start loading the probe rows against it. And it's possible that all parts will end up on disk, but this is known as a hybrid hash join or grace hash join. There's a bunch of other terms for it. This has been around since like the 80s or the 70s. Very standard technique. For aggregations, basically, we just start dumping partials, and then we do a merge back together of those partials. We do them in sorted order, so we can basically do a merge join. Very simple. So don't use this. They suck. So disks are slow. SSD is really expensive. Go look at the cost of SSDs in the cloud, and you'll be pretty shocked. And if you're not using local disk, you're spilling across the network, and it's even worse. And given the cost of these SSDs, you're probably just better off adding more memory to your cluster. Like you can add you can switch from the M's to the R's for not a huge step up in price. So like add more memory. The other thing people forget is it takes a bunch of CPU to take those memory data structures and write them to disk. Sometimes you need to compress them because your SSDs are too small. A lot of environments require you to encrypt them. Encryption is not fast. Even AES encryption is still not that fast. It takes a bunch of CPU. But the worst part is that this will slow down your queries. And what happens is like your query runs great, it hits the spilling, and all of a sudden it's like, twice as slow, 10 times as slow. And users are like, is the system down? Why is my query taking so much longer? So it really, really annoys users. Also, like you're forgetting like your users' time is money. Like you paid people to wait for results. That adds up pretty quick. So rather than buying disks, add more machines. Rather than wasting people's time, add more machines. If you can always like scale up your cluster. If you know when big queries are going to run, you scale up your cluster beforehand, then you'll have the amount of memory you need. So the other thing we'll talk about later is for the really big queries that you think need spilling, you can go and analyze those and hopefully figure out ways to make them use less memory. Very much related to all this stuff is, what if I have a really small workload and I need a really small cluster? Very small clusters are hard. And I define a small cluster as not as I only have 4 machines or I only have 1 machine. I define it as it can only run a single query at a time. In those use cases, like if the query grows a little bit, it can hit the bounds of the cluster and you can have problems. If someone else happens to be running a workload, like what do you do? Things, I run a big query and then someone shows up with like a medium query. They have to wait behind my big query. What if they have to wait an hour, right? That's not a good experience for people. And, things like Skew can really hurt because you're in this tiny silo and it's like, oh, something skews and it hits the edge of a machine. So they're really hard to deal with. Hopefully you'll have instead a bunch of concurrent queries that are taking up your cluster because you have a bunch of employees that are all running stuff at the same time. You end up with mixed workloads. By the way, very much related to this, I'm sure someone will ask is, hey, should I run multiple clusters? If you can run multiple clusters and not end up with like a bunch of small clusters and still have a good mix of workloads, then absolutely multiple clusters is great. They're easier to manage because if you have a problem with one, you could take it offline without taking down like all of your resources or like half of your resources. And I don't get into it, but splitting interactive workloads from batch workloads is actually a really good strategy. They just have very different configurations and setups. And so small clusters are really hard to deal with, and hopefully you can just have either more resources or concurrent workloads, and kind of avoid those if you can. All right, quick summary. Wow, I am running over. Okay, so quick summary. Don't treat Presto like Hive, Spark, your microservices, anything else. Presto is a big distributed compute engine using everything to get your one query done as quickly as possible. Upgrade regularly, super important. There's always moving improvements. There are performance, security, features, etc. Upgrade regularly. When we get into determining workload, really think about concurrency and mixing of different kinds of workloads so that you can have average kind of stuff laid out. You know, it's difficult when like all your workload is super memory loaded, or it's all memory loaded at one part of the day and then all CPU at another part of the day. Like, you know, you're going to waste resources. When you get to dividing your workload up into machines, favor a few bigger machines over smaller machines. Like, it will make your life so much easier. Bigger machines can really, really mask over the problems of skew, and you know, you get less overhead, etc. And never, ever, 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 ever spill at the OS. Don't do it in Presto. It's just not. I'm not a fan of it. If you have to do it in Presto, like, I guess you have to, but like, try to avoid it. Try to use dynamic scaling in the cloud instead. Last point on this is plan for growth. My experience is everywhere Presto ends up, and people start using it, they really like it and they end up using it more. Presto is really efficient, so it needs a lot less resources than you would have allocated to Hive or Spark. But it's really efficient, so people will ask more questions and they'll use it a lot more. So you're getting a lot more value out of it, but there'll be a lot of demand. Also, Presto can do things like join data sources from different departments that just weren't even possible before, so people will use it to build new things. It's not unusual to see Presto double or even triple every year. When we rolled out Presto at Facebook the last few years, we grew 27x in 18 months. We were like doubling every quarter or something. It was insane. It was really hard to keep up with. That's unusual, but like, you know, all throughout we were, you know, had dramatic growth in terms of people using it because it can do all these great things and it's fun to use and easy to use. So talk to your bosses about this. Make sure you have budgets for growth. It's something you really need to think about. All right, break time. Manfred, you there?
Of course I am. I'm not hiding. I'm just super busy trying to answer all these questions that are flying in.
Yeah.
So
and I'm going long.
Yeah, that's okay.
Sorry
well, I
about
mean,
that, everyone.
it's an interesting and complex topic, and there's a lot to say. So, you know, that's what it is. You're the one that has the knowledge to answer that. One of the questions that came up regularly or semi-regularly is, like in general, like we determine sort of like the workload and the queries on it and stuff, but then what do you use to figure out the load? Like I pointed them that yes, you can look at the web UI, obviously. Lots of stuff is exposed via GMX metrics, and you probably want to pipe them into some sort of analysis system. Is there anything else that you can suggest that people do, or what you have experience with that works well?
If you have the queries, it's pretty straightforward. You spin up a cluster, you're on the queries. You can look in the CLI or the UI. It'll tell you how much CPU time it used. It can tell you the peak memory, and those are your big numbers. You want to, you can do a bit more analysis, like you can run an explain analyze, which will tell you what each section of the query does. So we'll talk about that a little bit in the next section. as you figure out like, why is this query using these resources? Can I make it more efficient? But those are the big numbers, is how much CPU time it's going to use. And, you know, plan for some overhead, plan for growth, and, you know, leave extra space for things like skew and growth.
Yeah, no, that's good. So, but basically, even the CLI exposes those bare metrics. That's good to know, right? So,
Yeah,
CLI is generally very useful anyway.
Yeah, I think it shows more if you do like -- debug, more stats.
Oh yeah. Okay. Another thing that I
explain
mentioned.
Analyze is awesome. Sorry, explain Analyze is awesome. Like it tells you everything.
Yeah, Martin already covered that in his training slide. By the way, that's something that people ask. So, general to understand, right? We're gonna make this recording available on the blog prestosql.io/blog, and the other training sessions, and also the webinars that you'll see later in this slide deck are also all available. So, if you like want to rewatch it, or you want to take down notes, or like figure something out in more detail, just take advantage of that. It's all there for you. So let me just check if there's anything that we want to cover in more detail.
By the way, everyone just keep the questions coming, because this is a ginormous subject, and I may have even forgotten like whole areas. Like, we talked to a bunch of people and came up with a list of things they found helpful, but you know, we may be missing big areas.
Yeah, totally. Alec was asking an interesting question. That is, he says that it seems straightforward to tell whether your CPU limit, and yes, of course, with the CLI and stuff like that, you see that. But how do you tell if you're memory bound?
So Presto itself tracks the amount of memory that's allocated. You see that in the UI, so you can see of so much global query memory, I've allocated this much to queries. So you can see that at the general pool, and there's JMX stats for it. There's a bunch of ways to view the general pool. Then the JVM itself, you can go and see the JVM stats, and it'll tell you how much is being used of the total heap. Just keep in mind that those stats, how much is being used in the heap, they'll change over time as the garbage collector kicks in. So it's running in the background. So like if you sit there, it may go up and down even though like nothing has happened, because it's like allocating free space, etc.
Cool.
But the big thing to watch with the JVM is if you have like 100 gigs and the garbage collector's running, and it's running like 95 to 98 and then down to 95 to 98, it's got basically no working space. Your system's not going to perform well. What you want to see is like it'll allocate like a big chunk and then collect it. You'll see this kind of saw pattern as it goes through the thing, which gives you a sign that the working space is in that somewhere in that realm.
Oh yeah, that's good. So there's George asked a like actual practical question. I think I gave him the right hint, but I want to confirm with you. You know a lot more about this. So he says they have queries with lots of joins and windowing functions, and they run into issues where the node sizing and currently with 512 gig, which is pretty beefy actually.
Yes, very beefy.
So they run into issues with that. So would you recommend scaling, like adding more node memory, or scaling out? My guess was scaling out.
Scale out. Yeah. Okay. The other thing is you should look at there's a thing called the fades. There's basically it's another thing I didn't talk about. There's two ways that Presto can schedule queries. It can try to schedule queries so they complete as quickly as possible, which is called the all at once. So like we're going to start, if we just have a simple join query, we have a build and a probe and a join. We're going to start reading the build table, the probe table, and the join. We're going to start all this stuff at once. And that way, like the probe can start running and like filtering data sources and filling buffers while this hash table is being built. So as soon as the hash table is built, there's data ready, and it just goes plows through it, right? Well, there's a different strategy, which is called the phased execution strategy. And you can just search our docs for it or ask me on Slack. And what we'll do in that case is we'll start the build, we'll start the join, but we don't start the probe at all. And so then the build's building this hash table, and then only once this stuff is actually built and actually set up do we actually start these probes. Well, what that can do is if you have a whole bunch of hash tables or like a bunch of unions, what we're going to do is we're going to delay starting the rest of those till we actually have got these guys all going and they're all happy. And that way you can actually reduce overall memory. And it works pretty well. We used it in the batch system at Facebook. But it will slow down your queries because we're not actually starting everything all at once. So,
yeah, I mean, like you're making everything sequential to some degree, right? Like obviously it's gonna take longer.
a little bit more sequential. It's not bad.
Not completely. Okay, that's
most users won't notice it if you have larger queries. Like actually, if you have larger queries, they aren't going to notice it at all.
that's good. All right. Sorry, I have to ask this question from Will. That is funny. He's like, any advice on how to recover from a previous team's botched cluster sizing that basically went contrary to everything you said? Which is basically the common pattern, right? Like everyone like goes, oh, Kubernetes, lots of little containers and stuff. And that's what everyone tries to do. And then with Presto, you're like, well, that's completely the wrong thing. So he's basically asking, so how do you convince people that like think they know everything about the cloud that, well, that's not how Presto works? I mean, yes, you can show them the recording of this webinar.
Sorry. Yeah. So just tell that team that you show them this section, they're wrong and they need to fix it. And if they want more advice, they can come talk to me. I'm more than willing to talk about it on Slack and tell them that they're wrong. But that's one part of the problem. Then once you convince them and you go and you like right size your cluster and pack it better, then you have to go tell your users, hey, we're right sizing our clusters and everything's going to be more stable, and you do a bunch of marketing. By the way, do the marketing after it's already stable, because you don't want to do the marketing and then like figure out you made a mistake and then people are unhappy again because you'll look like a fool twice.
Yeah, so, also if you do the marketing first, then you get more users and then they're not going to be happy. You want to make sure that they will be happy, right? So that's
and also really good point. When you do this, over allocate the cluster for the next like 3 to 6 months, so you can change user expectations and be like, yeah, we figured out, you could just tell them that Presto has some new feature that made it better, so you're not actually taking the blame for it. Doesn't matter, like, and then market it, Yeah.
It's one of those things, right? Like soft skills are extremely important for engineers. People always forget that, but it's very important to communicate, market, and talk about what you're doing.
In this next section, we're going to talk about resource management, and all I'm going to talk about is psychology. Like, it's the only thing that matters.
Okay, well, with that, I guess we can start the psychology.
All right. Okay. I'm going to turn off the video again.
Yeah, that's hiding.
All righty. So, in this section, we're going to talk mainly about tuning your workload. So like you have this problem of like, okay, I went and did my cluster sizing and whoo, that's way too big and I can't afford it. What can I do about it? How can I be more efficient? These are actually very similar questions. So that's what we're going to try and deal with here. Keep the questions coming because this is a big area and I covered what I thought was the most common stuff. So how do I reduce the actual work that's being performed in the cluster? How do I make queries faster? So that's 2 parts, 2 goals to that. One, people just always want faster queries. They make users happier, but also faster queries can they make your memory more efficient because you're able to free up that memory for another cluster to use. So that is also an efficiency thing. And then you're clearly not going to have all the resources for everyone all the time. So how do we share resources, et cetera, across users? So this is a huge section that I'm not going to cover, which is query plans really matter. They can fundamentally change the performance of a query from taking like hours to taking minutes. You're going to have to watch Martine's training on this. Things like join order are really important, and how joins are organized. So in this picture I show here, I show the same join of 4 tables, and you can see like, oh, what I can do is, this is there a right side join, a left side join, and a bushy join. There's a bunch of research papers written on this. Again, like all the database research was done in like the 80s and some of it in the 90s, and a bunch of it in the 70s. But basically, you can start by taking your tables, joining them to, this is your build, and you can join 2 tables together and then feed that in and have that be the next hash table, and then join that, and then you end up with 1 hash table at the end. Alternatively, you could take, on the other extreme, all the hash tables in memory, and then you're basically pipelining through these processes. There's different reasons why you might do one over the other. Again, you're going to need stats, etc. But this stuff does matter and can change. Things like having these be distributed joins versus broadcast joins are like game changing. Like there are queries at Facebook where they would literally take 24 hours, and then you go and you look at them and you're like, this should all be broadcast joins. There's no stats, and it's picking a distributed join, and you do it, and the queries take like a half hour. Like, it's just totally night and day kind of things. So these things really matter. In David's training, where he talked about advanced SQL, there are constructs in SQL that if you don't know about them, you work around them by, so like if you don't understand how grouping sets work, what people do is they'll write a bunch of queries that union together aggregates over the same data with different grouping, and then they they join these together. Well, that's not efficient. That's not slow, and they're hard to write. And if you write it as a grouping set, they run way faster. Things like understanding how a top and row number works, like there's special optimizations in the engine for it. Hey, this is a big deal. Count of a column, when you say filter by where name equals 10, is dramatically faster than count of case name less than 10 1, right? Versus null, right? So this is actually a big structure. Depending on your query, this could make your query be significantly faster. Like, we had a system at Facebook where they switched to this, and like we were able to reduce, this was a totally custom application, so don't expect this, but we're able to reduce the CPU usage by like 20%. So there are a bunch of things like that. Sometimes the optimizer, sometimes the structures were able to automatically convert to the other structure. Sometimes we actually can't do the conversions because the language has subtle side effects in it that you're not really aware of, and so like we can't actually make auto conversions. Sometimes like the rules haven't been written, so the optimizations aren't there. Things like these approximate functions, distincts are doing a bunch of count distinct or aggregate with the word distinct in it is unbelievably expensive. You basically have to go and figure out, hey, what are all the distinct items, which means you have to actually at some point have basically all the distinct items in memory so you can say which ones are not distinct. And so you end up doing like big distributions. It's really complicated, super expensive. So you should be training your users to know about approx distinct, approx percentile, approx most frequent new. These will make your queries go from being crazy slow to being like pretty much instantaneous. They're awesome. Use them. Now, you don't get exact answers. You get answers with an error bounds and a well-known confidence, and that's normally good enough for just about everything. One technique which we're going to talk a little bit more about that wasn't covered by those is pre-computing. So this is a really common technique. People talk about this. For expected queries or regular queries that have a common shape, you can either, if it's like the same query over and over again, you actually just run the query, you put it in a fast store, and then you just use that pre-computed result instead of actually running it each time. So that's like, if you can do that, that's really easy. It's simple. If you know they're going to run this query every morning, you have a cron job that just goes and like pre-computes the results. Another easy technique is to put the source tables of your common queries into a faster store, faster format. It's shocking how many people show up with queries and you're like, their query's really slow, and then you find out they're using, I don't know, text files with JSON in it. That's like, well, every time I read that, I have to parse a text file, I have to parse JSON, find the one column you're interested in that ginormous JSON document, and then read it out. Okay, well, how about you switch that document to be an ORC file, and then I can just go and pick out that one column. It can make your queries, 10 times faster, no problem. So like, or if the data sets are really small, copy it into MySQL and use MySQL. Like, don't underestimate like just making a small copy for stuff that's really common. So like, that's a form of pre-computation to me. A little bit more difficult. If you look at a bigger query, you do an analysis, you run like explain analyze, which Martin talked about in his presentation, and you figure out one part of it's expensive. You can just compute that one part of the query and store it, and then reference that table instead of the full subquery. So that's another common technique. Requires changes to the queries in the application. So a lot harder, because it requires a bunch of changes, are things like storing partial aggregation. So, oh, I have this dashboard that's doing counts by users per week or something like that. Okay, well, every night I can take the daily count of users and store that, and then I rewrite my queries to do a sum of the daily counts. Very common technique. It's a bit harder because you have to change the application. You have to understand what partials they're going to want to do. Typically, you're doing like drill downs in the dashboard, so that requires a bunch more changes in the dashboard. It's more difficult to do. It's very powerful if you can do it. Like, we had entire systems at Facebook based on Presto that did this. We had custom applications to do the roll-ups and maintain them for it. But like, they are the difference between literally Facebook couldn't afford to run the system, and that's a very expensive system, to like, oh, it's actually not that bad. So very powerful, but requires a lot of time, require application changes. Lots and lots and lots of people will be like, oh, you just sample the data. Sampling is unbelievably hard. It looks simple, and lots of people use it, and they get answers, and their answers are 100% wrong because most people don't understand statistics. Like, I won't do sampling of data. I know a lot of statistics. I don't do sampling queries because it's too hard for me to do. I know enough to know this is crazy hard. And people who actually understand the statistics, they're rare and they're very expensive. So in my experience, it's better to just buy more machines than it is to try and go and hire one of these statistics people. And the reason being that they're only going to deal with a certain part of your system. Oh, and if you hire two of these statistics people, they'll disagree on how the sampling should work, by the way, because it's an art. So I strongly suggest sampling. That said, we had a system at Facebook that had tons of sampling to do A/B testing of queries. And we had some world experts in statistics to help build that system for the company. And it was very effective. But of course, it did take us 2 years to build it. So avoid it in general. Another really important thing with workload sizing is understanding the data store you're going to connect to. So for most of the rest of this presentation, I'm going to talk about Hive. And the reason I'm going to talk about Hive and Hive data sources, I'm talking about, Hive is kind of an old term, but I've been doing this for a while. I'm talking about like object stores. So we're talking S3 with file formats like Orc and Parquet. This is generally referred to as the Hive data source. And the reason we do that is because Hive actually defines this specification. Well, it's not a specification, it's convention about how we take files and we lay them out in directories and things like that. The reason I'm going to talk about Hive is yeah, go ahead.
And importantly, that means you end up using the Hive connector to query HDFS, S3, Google Cloud Storage, Amazon Azure Storage, like Azure Storage, whatever it is, you're always going to end up using the Hive connector, and that's the metadata is always stored in like some Hive meta store, which can be the Hive meta store itself or Glue or whatever. That's why. So just
But by the way, the reason that I'm talking extra about this and Manfred jumped in is because it's a super common area of confusion. People are like, oh, you're sending queries to Hive. Presto doesn't use Hive at all. We read the data directly. We do all the computation. This is why this connector is typically the biggest CPU user in your whole cluster. It's the reason why you're building a cluster, a big cluster, and you're growing it out, is because you're reading data from object stores in Hive file formats. And we're going to read it directly, and it's highly parallelizable. The data is really compressed on the network, so that makes actually the network more efficient, but that means we have to use a bunch of CPU to decompress it. And typically in a well-run system, we're going to be completely CPU bound based on, the Hive data we're going to read. Might be network bound. We'll talk a little bit about that. The other common data sources in Presto are what we call JDBC-based data sources. So these are data sources like we're going to connect to MySQL, Postgres, SQL Server, Redshift. We have a bunch of other ones. And there's ones that you don't think are JDBC based, but they actually are. Like, I think that, anyways, I'm not going to speculate. But what's important about those is that we have a Presto connector that's connecting to a store, but what we're doing under the covers is we're interacting with their JDBC driver. So we're building a query text and we're sending it to their JDBC driver. We're opening up one connection to the MySQL or Postgres, and then we're pulling all the result data back through that. So this ends up being not particularly fast. Like, first of all, we're getting uncompressed data over the network, where we have a single connection. We're not reading in parallel, which means it's hooked up to like a single CPU on the Presto side, may get fanned out after that. But basically your bottleneck is like, don't expect to read more than like 5 megabytes per connection. Now there's one connection per table we're reading in the query, but like it's not super fast. Starburst has a bunch of these connectors rewritten so they're parallel and has other things that are parallel, so you can get better performance. But again, they're still limited to like each connection is going to be like 5 megabytes, and you might have 10 or 100 of these connections, but there's limits. Like, and you don't want to like have 100 connections to Oracle because you get charged by the connection to Oracle. At least I think you still do. I don't know. Anyways, and there are a bunch of other connectors in Presto. Most of them are either single threaded like the JDBC connector, or you're connecting to data stores that aren't particularly that big, so they aren't going to use a lot of CPU. So that's why we're going to spend basically the rest of this talking mostly about Hive connectors. Now, if you have questions about the other one, just ask Manfred and I'll get back to them. So I'm going to talk about how data is organized in Hive and how that affects queries, because this has a huge effect on the amount of work you're going to end up doing in your Presto queries. So Hive has a bunch of ways of organizing data. Presto, as an engine, can take advantage of the physical organization of data from connectors. So if the data is partitioned and Presto knows about it, then we can do something about it. If it's sorted, we might be able to take advantage of that, depending on the guarantees the connector can provide to us. And we'll have different query plans that are much more efficient because, if the data is already partitioned, then we don't need to repartition it, for example. So what Hive calls partitioning, and I should be really careful about that because Hive has very specific terms that the rest of the database community doesn't really follow. So Hive has this very unique partitioning strategy where basically, let's just back up. Hive writes everything to files in your object store, your HDFS or S3 or GCP or Azure's thing. Those files can be organized into directories and the rows can be organized into different files. So the first technique that Hive added is called partitioning, in which case each value of a column is written into a different directory. So the most common example of this is date. So like every table at Facebook was partitioned on date. So like the page views from the users from yesterday are all in a directory by date. Actually, they were by hour because there's a lot of page views at Facebook. But things like, the orders you get for yesterday are in a directory that has the name of the date. You can use multiple columns, but typically this is one set. So divide it up into directories. The nice thing is that this is a whole thing. If you're searching for the last 7 days, you know which directories to go look at. If you want to delete a day's worth of data, you just go delete the directory. So this is almost always used for that sort of design. Bucketing is a little bit different. The data is, you're basically hashing the data on a column and dividing it into files, not directories. And you can use both of these at the same time. All right, so I just talked to this. The big advantages of Hive partitioning is it can reduce scan size. So almost every query at Facebook was, I'm gonna go look at yesterday's data or the previous 7 days worth of data. We would only go look at just those directories and just those files. So the alternative of this is like, hey, I don't actually have stuff partitioned by date. Someone runs a query that says, select me the last 7 days, and you have 2 years worth of data. They're gonna read 700 files to find 700 days worth of data to find 7 days worth of data. So this would cut that query dramatically. So that's the really big advantage of partitioning. Now, you only want to apply this to lower cardinality. Data is a very good example. A Boolean value wouldn't be particularly helpful, true or false kind of thing. But if you partition by a few of those columns together, then you might end up with something that's a reasonable cardinality. If you end up with something too small, then you end up with this small file problem, and we'll talk about that in a minute. By the way, in Presto, we can apply basically functions to these because you actually know all the values. You can enumerate them from the meta store. And so you can provide like arbitrary functions. This doesn't work great. This works great if you have things that look like this, but if it's like this, and then like some other expression that doesn't involve the partition columns, like we can't solve for that and just prove it matches or doesn't match. But it's very powerful for eliminating data. Bucketing is another interesting technique. Basically, the most common use of this is you're going to bucket by user, and that allows you to say, hey, I'm looking for user 42 and 55, and I may have divided all my users into 1,000 buckets or something like that. And I know user 42 must be in bucket 6, for example, based on the hash function. And so you only end up reading, like in that example, 1/1000th of the data. So very powerful technique. So the thing that becomes even more powerful is Presto. If you enable this flag, bucketed execution enabled, it's not on by default. What we can do is if you're doing a group by or a join, but I'll just talk about group by. If I'm doing count by user, then if my data is bucketed by user, then I can know that all of the users, all of the data for this user is contained within this one bucket. And so what we're going to do is we're going to take that bucket and we're going to run it on one machine. And we don't have to redistribute the data to find, all the data for the user across all the buckets. We know the user are contained within that bucket. So it removes redistribution costs, which are huge. Same thing can be applied to joins, which basically kind of turns it into a version of a broadcast join. It's super efficient. It is dangerous though, because you have to watch out for skew. Like one bucket could be dramatically bigger than the other ones and not actually fit well. And it could make queries slower because you're basically, each bucket is managed on one machine. And if a bucket is really, really, really big, then it isn't going to be distributed across machines and you don't get to use all the resources of the cluster. So be careful with it. That's why we don't turn it on by default. By the way, bucketing isn't super popular. It takes a bunch of work. You can only bucket in one direction, so it only makes some queries faster. It can make writes a little bit slower, etc. All right. Flat out, use Orc or Parquet. Everything else is slow. And if you get to choose, pick Orc. It's dramatically faster. I know Parquet is more popular. Parquet isn't particularly a great format for relational databases. It's spectacular for document stores. Basically, the first format came from Google's Dremio paper that described how you can efficiently store documents in a file and quickly access parts of those documents. But Presto and the rest of these engines running SQL, they aren't about documents, they're about relational databases, and these are tables. And although you can think of a table as being a document, if you design directly for a table, you can have even more efficiency, and Orc is designed for that. That said, Parquet is fine. Always compress your data. Uncompressed data is actually slower because you get killed by the network, you get killed by the IO. So just compress. I actually recommend that you use a high compression algorithm. I recommend Z Standard, which is a new compression algorithm. It is better than zip in every way. It's dramatically more CPU efficient. Like, just go look up the benchmarks. And it's dramatically more efficient on read. And you're going to spend a huge portion of your Presto cluster decompressing data because you're going to be running a lot of read queries. And Z Standard can reduce that dramatically, like more than half. It's crazy. It's really, really well designed. And it's brand new and it uses new math, but it's also just optimized for modern CPUs. If you're going to use a low compression algorithm, use LZ4 over Snappy. It's just, again, better in every way than Snappy. Never use LZO. It's not a very good algorithm. I'm not going to go into details. I know all these because I worked on the Java ports of pretty much every one of these algorithms, except for zip. So Orc files and Parquet files are designed to be read efficiently. That means they're expensive to write. But they're very powerful because you can go and, like, you're typically not running select star from table. You're saying select these 3 columns out of these 20. And we don't have to read and decompress all the data to find those 3 columns. That's how all of these work. If you have lots of columns, so you don't have 100 columns, you have 10,000 columns, what's going to happen is you end up with, the system's going to take, like, I don't know, 100 megabytes of data and then divide it up into columns. But then since you have thousands of columns, each one of those is going to be really small. You end up with small IOs. every IO takes latency, it slows down the system. So don't have 10,000 columns. Like 1,000 columns is fine, but try and stick to lower column counts. And this, by the way, includes all nested columns because they're just unwound in both Orc and Parquet. Sorting can help make these a little bit faster in terms of like skipping sections. You know, be careful, you can only sort in one way, but if you're gonna run the same queries, sorting can be a big advantage.
Dixon is asking, by the way, if you have an estimate on how much faster Orc is than Parquet, percent-wise. I don't know.
Depending on what you're doing inside of Presto, it's more than 2x. So, and saying that, Parquet is not slow. So if you compare Parquet to everything else is really bad. So yeah, use Orc if you can. It's just dramatically better. Also, by the way, when you see benchmarks of Parquet, of Presto, and they're like, oh, we decided to randomly choose the Parquet format, you know that it's benchmarking and they're just trying to make Presto look bad. Because everyone knows that if you want to get peak performance, you're going to use Orc on Presto. So file size is a big deal. Anyone running an HDFS cluster will tell you this, but I'm going to be a little bit more specific about Presto. Basically, any file less than 8 megabytes is small, and our Orc and Parquet readers are going to look at that and go, I'm not going to ever get efficient IOs out of this, and it's literally going to read the entire file into memory. So all of a sudden, that awesome technique of like, oh, I only need to like read 3 of these, 100 columns, that's out the window. Like we're loading that entire file and all the files that are like less than 8 megs, we're loading those directly into memory. We still will like only decode the sections we need, but you're paying the IO costs. In terms of like the other formats, like you may get really small IOs, like other systems like Hive and Spark, like they can just grind away at these small files because they don't actually have, we spent a lot of work in Presto doing IO optimizations, mostly because the IO systems for our storage at Facebook were not good. So we have, I spent like 2 months writing an IO planner. Lots of small files has the problem that you have lots of file names you have to list, and listing files is slow, and it's really slow in S3. And so having bigger files will make that much more efficient. You also get bad compression. Basically, just avoid small files. And by the way, I bring this up because this is actually a common support question when people have that we run into at Starburst, and we're like, okay, show me your files, and they're all like, 1K files, and you're like, well, that's never going to be fast. I mean, rewrite the table, and then it's like dramatically faster, like 10 times faster in a bunch of cases. So make reasonably sized files. Shoot for 100 megabytes. Now, this is a new thing that I've seen recently, so be really wary of bad Parquet files. So I saw this with both Snowflake and Greenplum. I think Snowflake may have fixed this, but they'll dump out these like, oh, export my data to S3, and they dump out these things. They look like good files, but then if you take the Parquet tools and you run them, the files are divided into 4K chunks internally. That means like your 1,000 columns or your 100 columns, like all together, all the rows is like 4K internally, so it's microscopic, and this will kill your HDFS, your Hive and Spark. Presto does an okay job with this. Like we actually wrote optimizations around this, but these files are bad. They'll never perform very well. You have to rewrite the data. So if you're getting dumps from non-Hadoop systems, run the Parquet tool and see what they actually spit out. And then go and complain to the vendors, tell them they don't know what they're doing so they actually fix it, because it's really bad for everyone. All right, so one way you can make your system faster is rewrite your table with Presto's ORC writer. We have a custom ORC writer. It's not the same one used by Hive. It's optimized for files that are easy to read. And so we do extra organization that they don't do in the Hive writers and the Spark writers, and you're going to get better files. Okay. The other thing is that at the same time, we will automatically collect stats. Whenever we write tables in Presto, we collect stats. So now your stats are actually there. You can also switch to Z standard, which is a much better compression algorithm. You can also do partitioning and bucketing, etc. Consider using the scaled writers where we'll automatically size the files. Anyways, consider this. It can be a big performance win, especially if you look at it and you're like, these files are just bad. Not always an option, but at least you could rewrite like the most common data sets used. All right, so wow, I guess I'm at, should I cruise through this stuff, Manfred? We got making queries faster.
Totally.
I guess so. All right. Okay. So basically, a lot of this presentation building up to this section. Look at your query plans, look for approx functions, pre-compute the data. All these things make your queries faster. All right. Now, this again goes back to I help a lot of people on Slack. So one thing is, I'm going to ask the obvious questions like, are you running out of CPU at peak times? If so, add more machines at peak times. Are you running out of network? Figure out why. Maybe add more machines. If you're in the cloud, like you have fixed networking sizes. Your storage system can become saturated. We have this problem all the time at Facebook. And if that's true, there's actually nothing you can do other than to let your users know that the storage team messed up your cluster. Unless you happen to be the storage team, then you need to go add more disks, or flash. But that will take a long time. The Hive Metastore runs on a database. People forget that that database will run out of CPU and it will slow literally everything down. So look at this database. This is a big deal. All right, so now you're like, okay, I have a query, it's slow. What do I do? All right, read the query text. If someone says my query's slow and it's like 5 pages of query text, hand it back to them and tell them they need to go and give you a smaller reproduction because no one can deal with that. Like I won't deal with it. Like support people won't deal with it. Have them go and like take chunks of the query and start experimenting with it. But big things to watch out for. Are there a million distinct clauses? If so, teach them how approx distinct works. You know, the approx count distincts and things like that. Do they have a ton of unions? Did they happen to not use union all? If not, they're actually doing distincts. Distincts are slow. Teach them how union all works. Do they have did they write grouping sets by hand? If so, teach them how grouping sets works. This is, by the way, super common. I bring these up because these are common things that Facebook engineers would bring me. Do they have a million regular expressions? Regular expressions are CPU intensive. Do they have a million other expensive functions? Very common expensive function is JSON. People are like, oh, I didn't want to create columns, so I just created one column that has a 5 meg JSON document. Well, it's like, great. So now every time I run a query, I have to parse your 5 meg JSON document for every row. Pick out the columns you want to use and write a real table. I mean, this is shocking, but like people don't realize like every single query is going to go through the same cost, and you could do that once instead. Then run explain. Did you get the query plan that you expected? If not, or if you don't know what I'm talking about, go watch Martine's training. Again, look for tons of mark distinct operators. That's the same thing as the union all or the approx distinct I just talked about. Look at the join types. Look to see if there's stats. Martine's section training will talk about all that. Explain, analyze, runs the query, takes all the stats, and then integrates them into the explain plan. So you basically run this, it'll run the whole query, then you go and you look for the most expensive stage and the most expensive operation by CPU time. If it's a table scan, ask if it's reading too much data. Like, could this data be organized better? Like using the Hive. Did push down work? Are there like push down filters of like, I'm only reading certain partitions? Did they forget the partition filters entirely? That's a common mistake by new users. There is a flag that you can kind of enforce people to have partition filters. It's in a fairly recent version of Presto. If it's a join, look at the rows before the join, after the join. If they have 10 times as many rows, figure out if they actually wanted an expanding join. Most people don't know how to write joins. Most people expect a join to be like, for each input row, I get an output row. They have like 1,000 times more rows. Like, that's probably not going to perform and be really slow. So like, just look for it. Really easy thing to catch. Are the filters crazy expensive because they're processing JSON? My favorite topic. And then if it's not one of those, then it's likely to be a function or something like that. That's really expensive. If not, just go ask on the Slack channel why, this section would be expensive. Someone should be able to explain it to you. But basically, take that one section of the query, run it, measure it, try changing it, see if you get the results you want. That's kind of the experience that I go through on this. You can always ask, can I just throw more hardware at the problem? Well, my easy answer is, well, try it. Spin up some more machines and see if it gets faster. Like, it's a lot of times easier just to, spin up a few machines for a couple hours and see if it improves things. And if it does, great. So remember though that speeding up has limits. So again, back to our earlier picture, if I only have 8 splits and I have 16 cores, like, you ain't gonna make this faster. Like, these are just gonna sit here idle. There are gonna be other things that make things idle, like IO, things like that. We'll talk about that in a second. But remember this: if you have a lot of concurrent work, this is great. You can throw more hardware at it. That's normally pretty easy. By the way, if you want more splits, you can force more splits by telling Hive to bucket your table and partition it, but watch out for the small file problem. So there are techniques to be like, I want to have 10,000 files. You can do that. Just be careful. All right. So you can't throw more hardware at it, which is another way of saying I threw more hardware at it and now I'm not utilizing it. Why not? So you have plenty of work to do, but you have idle CPU. So you have things queuing up. You're just not able to use all the CPU no matter how many concurrent queries you throw at it. So very common causes, and these are almost always Hive because the other systems just work because they're just connecting like JDBC, to MySQL over JDBC. The Hive metastore can be slow, in which case you can't list partitions, and then you have everyone sitting there waiting for data out of the metastore. And this is almost always because the database is overloaded. So go look at the database. Presto has JMX stats for every operation for the metastore. We have these because the metastore at Facebook sucked, and we need to figure out exactly why it was broken. And so we have tons and tons of stats around this. Just go look through JMX, and you should be able to find the ones that are slow. File listing can be slow. It's actually normally pretty slow in S3, but if your name node on your HDFS is overloaded, it could take a long time. If you have tons of tiny files, you might get throttled by S3. There are JMX stats for this, and you can look through and figure out how long file listings are taking. If the reads are slow, almost always tiny files. It could be the network's overloaded. It's more rare. If it is, check to see if your files are actually compressed. If they're not, go and compress them, because then you'll use like 10 times less, 1/10 the amount of network, and you won't be network bound anymore. And there are JMX stats for that also. Finally, it could be Skew. We talked about this early. Skew is actually pretty hard to fix. You basically have to change the query. So again, very much look for the, half my users have user ID 0. If so, either filter those out or do something like, if user ID 0, generate a random number to distribute that workout and join it back together later. You can do tricky things like that. Presto isn't going to handle this automatically for you. You can try to work around it by increasing task concurrency, increasing the threads that are available to a query. Sometimes that can help a lot. You just be like, great, we're going to use 32 or 64 threads for task concurrency. Bigger machines can help. So the stuff I talked about before. So almost all of those problems earlier can be addressed by some form of caching. Caching, you have to be really careful with. People think it's a silver bullet. It is not. It has downsides in kind of all the cases. You can cache the metastore data. This works really good, but be aware that when a new table shows up or a new partition, you aren't going to necessarily see it until the cache refresh comes in. So go look at these options and you can kind of set some expectations for the caching. It can be, very powerful. This is normally where we start if there's an issue with we'll turn this on if there's an issue with the metastore and just get users used to it. Listing, this works pretty well, but again, be careful, like you may miss new files. That's normally not a huge deal because most systems, they're not running inserts into existing directories. They'll use partitioning whenever they're creating new directories because when you're running an insert, each insert would create a new partition. And the reason for that is more about data management. So when you run an insert, you want to know what was added so that if later you figure out there was a problem with that insert query or there was bad data upstream, you can go find the downstream partitions and then delete them and rerun them. So most of the big companies are managing that way, in which case they're never inserting into an existing partition, in which case file listing caching doesn't have a huge downside. We recently have added this file data caching. Be careful with it, it's new. It's not as tested as like the previous 8 years that we worked with this stuff. It requires local disks on Presto, so don't cache to a network disk. Like, that's not awesome. I mean, I guess you can, but be aware it's going to take away from your network. Also, you're caching to the Presto nodes, and it's spread across the Presto nodes, so the system will try to place work where that cache exists, but if it's wrong, you're still using the network between the Presto nodes to fetch data. It requires additional CPU, memory, network, a bunch of other things. So like you'll need bigger nodes to deal with this, and they need to have disk of some kind. And most importantly, S3 is actually pretty good. So this actually doesn't help very much with S3 in most cases. Instead, like if you're having issues with S3, it's probably due to small files. You probably want to just address the small file problem directly instead of messing around with caching. This can be a dramatic help in Azure today. And I'm not sure about GCP, I haven't seen it yet. All right, sorry, we're a little over. I got one slide on resource groups, sharing resources. So you're not gonna have enough resources to run everything. Well, you're likely to not have enough resources. And so for the resource group, for the resources, when you're setting up resource groups, which defines queuing basically, focus on human psychology. You're going to focus on the happiness of your user, not computer science, not what you think is right as a programmer or an admin. You're trying to make users feel that they're getting the experience they want. So match their expectations to the experience they're getting. So small, fast, trivial queries like explains should run immediately. Set up a special queue for explain queries and have them jump to the front of the line and always run. And then the system will feel responsive to people. you can set a queue up that is the fast queries, and you tell people if they add a client tag that says this is fast, and then you give them like a 5-minute limit for those queries. So if they're fast, great, they run. If they don't, they fail, and then they blame themselves. People hate waiting in lines. So if you can, have enough resources so that everyone can run exactly one query. They'll have dashboards that'll have like 10 queries in it, but as long as one's running at a time, they feel the system's responsive, and then they don't blame you for waiting in line. They're like, oh, my other query's slow. I have reached my limit. And so like they won't come complain to you. Same thing. Another great trick that we used is we would divide people into the group of the people they work with. And then we would say, hey, your group has these resource limits. And then we'd let everyone in that group know which of their coworkers are running queries. And if the queries are big, then they come and they talk to their coworker instead of talking to you, and then they start managing the resources. Now that of course works until they're actually just completely out of resources, but like it's a very good way to like lean on the social dynamics, have them like work with their people on their team. Also give them the rights to kill each other's queries. Like they'll work it out. And when they come to you and they're like, oh, why can't I run queries? You're like, oh, Bob in your group is running a really huge query. Oh, well, can you kill that? No, but here, let me show you how you can kill that. And then when Bob's query gets killed, they go and they talk to the person who on their team, not coming back to you. Like you don't want to be the arbitrator, so don't kill other people's queries. Make the other coworkers kill them. So, bunch of psychology. That's really like I drill that into the heads of everyone who works on this stuff, and the people who wrote the code was human psychology is what we're trying to deal with here. If it's a batch system, life is easy. Just treat it like computer science. All right, Manfred. I can't hear you, Manfred.
Looks like I'm gonna have to rescue you. You have taught us a lot again today. Amazing. I've been trying to keep up with the questions, and we've been doing pretty good. I'm gonna just do one question just so that you get a break. This was amazing. The one question was from Dixon. He's saying that they have a long-running cluster, and after about 2 weeks, it sort of like starts degrading and destabilizing. So is there anything you would suggest of like regular reboot, regular restart of nodes or anything like that? Or is there some issue under the hood that they might have?
So we actually at Facebook, we would upgrade whenever a new release came out, and they come out about every 2 weeks. So we weren't typically running clusters that long. If you want to run a cluster really that long, just have a system that every couple of days takes a set of nodes, and there's an API to tell the nodes to shut down those nodes, give them a good time to shut down. They'll need to be longer than the longest query, and then start up some new ones. So slow them every few days.
That's a good point. That's actually a question that came up also from someone, if you can do graceful shutdown, and basically it just boils down to looking on that API endpoint until there is no query running, then you can shut it down and you just take some out of the pool, and presto, the coordinator will know, right? Like it'll automatically know that.
You tell it to shut down, and it tells the coordinator, hey, I want to shut down. Please stop scheduling work on me. And then after the last query finishes on that node, there's like a small grace period, and then it'll shut down. So, yeah.
Cool. Well, I think we have to wrap it up. We've gone over time again. You're terrible.
Sorry.
But that's okay. I'm sure everyone is learning a lot, and actually everyone loves it and appreciates it a lot. Just like in the previous sessions, in the training series, we had the class from David and Martin, which were covering advanced SQL first, then the query processing Martin, and then securing Presto with Dain last time. All of those are available on the blog, and this session will also be available on the blog. So prestosql.io/blog is where you see the posts, and you're in the list, you scroll down, you see the videos, and there's also links for the slides. In the same place is also where you can find the Presto Summit series, where you see what's practically happening at companies like Zora, Treasure Data, Pinterest, and also in the State of Presto, we talked about what's coming up in Presto. Some of those things already happened because we already cut another release just again yesterday. So the the state of Presto is advancing fast and changing all the time. If you want to keep up, prestosql.io, prestosql.io/Slack is where you find Dain, Martin, myself, David, all sorts of other pros that are working on Presto and using it all day, every day. Also, make sure you go to the Starburst website to get a free copy of the book I wrote with Martin and Matt, Presto the Definitive Guide. You can get a free digital copy, and you can also find us on Slack if you have questions around that. And I think we have to just wrap it up. It's been amazing. Go to Slack to find any more answers and questions for us, and we'll see you next time.
Jump on Slack to ask any questions. Sorry, I went a little long.
Yeah, no, it's all good. It was amazing. All right. And with that, it's a wrap. Thanks, everyone.